Welcome to the course Material Selection in Mechanical Design. Today's topic will be attributes of material, and I would like to talk about these attributes in the form of a case study. So, let us start with an interesting case study which will help us to understand that what is called the attribute of a material. The case study I have chosen is a simple case study to see that how the material is evolved for clock design. You know, clock is very ubiquitous. Even I am having a watch here with me, right? So, starting from the beginning of civilization, there was some or other attempt always to measure the unit of time. And in fact, the name of clock, I will later on tell you that something interesting what we call ghadi here suggests that it has a connection with the way we would measure the time, unit of time. Now, it has a very rich history, and it starts from before Christ, maybe 1000 years before Christ, and this study, this field is called the field of horology, okay, the field of measurement of time. And what is horology? According to Merriam-Webster, horology refers to the science of measuring time. So, science of measuring time, that what science I am going to use to measure time, and also the art of making instruments for indicating time, both of them. So, it is both science as well as engineering. In the horology of the clock making evolution, you will see that there are at least 6 distinctly different phases. There are many continuous evolution of it, but there are 6 distinctly different phases of material evolution from the materials point of view. How the clock is designed and redesigned again and again with the evolution of material and with the evolution of science of time measurement. So, let us look into that. What are the 6 different phases of horology? The first phase we will call it as the ancient phase, okay? And in that phase the measurement was based on stone like granite and wood. So, that was the first phase of time measurement. How? I am coming to it. The second phase is the medieval phase, when the use was limited to wrought iron. Then there came the Renaissance phase, when we started to use both brass and steel. So, you see the evolution of material has taken place. And then the industrial phase, where it is steel and some gem like ruby. And of course, the modern age came, where we have many other materials, alloys of titanium, not simple titanium, then ceramics, then silicon. Those are the elements of modern age clocks. And finally, if we look at today, if you look at your own hand, maybe you will find that you have a smart watch which has silicon, which has bulk metallic glass, which has smart materials. So, this entire evolution of material and the evolution of the science of measuring time has grown hand in hand, and we will try to figure out this fantastic journey together. Now, when we think of the ancient way of measuring time, what we always think of is a sundial, right? So, what does a sundial do? We know that it measures simply that the position of the shadow, okay, as the sun is, as the earth is rotating the sun, and we know that in 24 hours we complete the full revolution, and then in 12 hours the sun, of course, around that time the sun definitely will set. So, starting from the morning till evening, as long as the sunlight is available, which will vary, and you are going to get the position, change of position of this shadow. And so, from there you can measure that what time it is. Depending on the month of the year, this position will be shifting and the duration will be shifting. Now, this naturally, in order to do this, you have to have a time measuring unit which will be exposed to the outside environment, because sunlight has to reach there and you have to get the shadow. So, the material you have to use has to withstand all the forces like the wind force, the rain, and as well as the heat itself. So, they are generally very durable materials like granite, like limestone, marble, sandstone. These are the materials, along with maybe this section would be made of wood. So, the two things together placed a great role in history. And of course, another important thing you have to keep in mind, that whatever you are going to use in the heat, it should not thermally deform much. So, it should have the high dimensional stability, which almost all of these stones, they are either metamorphic stone or igneous stone. So, they can withstand the high temperature. Also, you keep in mind that this system would not work when there is no sun. That means neither in the night nor in the presence of cloud, etc. In such cases, what are we going to do? Okay, one solution of course is if we use a water clock. Okay, water clock also is known as clepsydras. Clepsydras means stealing a material. Okay. So, as such, in the water clock, what you have is that you have a unit like this, which has a small sort of a orifice in it, and then you place it in water, like you can see it here, and gradually the water is going to fill up, and once it fills the whole system, then it is going to sort of submerge inside, it is going to drown. So, then you have to replace this whole system by another empty one, and generally this sort of starting from the beginning till this end of the process, when it completely goes down, this would be taking approximately 4 hours. And in Sanskrit, this hour is nothing but ghatika, and it is from there the word ghadi has gradually been derived. So, that was the way the ancient time people in Nalanda, for example, used to measure the time. That means there will be a student who will continuously keep an eye on when this whole thing is going to submerge. And then once it submerge, you have to refill it again, you have to keep an empty bowl again. Now, naturally this whole thing then has to float, and so it is made of copper and bronze, because you can make it, because of the use of copper you can make it thinner, and then you can get a bowl shape out of it. So, that was the material requirement. With respect to the change in weather, these time variation would take place. So, accordingly one has to sort of adjust the timing. So, the way you can do it is that you can adjust or calibrate it with the help of a sundial. Whenever the sun is present, you can measure hour from there and check 4 hours, and then accordingly you calibrate the amount of water based on the season. So, that is how you can always reset the clock. Otherwise, there is no other external power requirement there. Of course, there later on, because the water handling may be an issue, so later on there came another clepsydras. So, that I will show you now. So, this is an hourglass. As you can see here, the time period of an hourglass is highly dependent on the external environment. In a normal hourglass, you will see that the time that it is going to take, let us say for this one, is for a specific time period, which is like about a minute in this case. However, the same time duration will get affected if there is the presence of a magnetic field. Like in this case, I have kept matrix, and then you can see that already the flow is stopped, and if I remove the magnet, again the flow is taking place, and I put it, the flow is stopped. So that means the effect of presence of magnetic field, variable magnetic field can actually change the timekeeping device. So these are some of the sort of shortcoming of the type of this type of time measurement, which can get affected by the environment. And so this is the system as another dry system, which can be just an alternate clepsydras instead of water filling, this time the sand evacuating from the top to the bottom chamber. Now we come to the medieval and the Renaissance phase. Okay. So now what were the problems with the earlier systems? Well, the problem is that you have to have a person who is attentive constantly, that when this change is happening, okay, and that of course as the human civilization become busier and busier, you cannot have it. So then people started to design the first type of a mechanical clock. So that is the first way of a mechanical clock, and you see that is the time when wrought iron people have understood, okay, that how to create the wrought irons by melting irons, and then from that by casting the iron how to create pieces of things using the wrought iron. Now the one important thing that helped there is that if you have an escapement gear, okay. So what is an escapement gear? If you look at the right side animation, it will be clear to you that in case of an escapement gear, you see that if it gets heated every time, like this left hand one is hitting, so it is moving by a finite amount, and then it is stopping in the right hand side. So every time you can divide the entire time of rotation into certain finite duration with the help of it. But then you need to hit it in a regular manner. So you need to have some kind of a measurement of the time, and that measurement of time came from Galileo. Though Galileo actually thought of it that is in terms of a pendulum. Okay. So what he observed in pendulum, I can show it to you. The relic of it is still there in terms of the metronome, which we use for many musical systems. So let me show you first how a metronome works, and then I will show you how Christian Huygens have assembled these two ideas together, the metronome with the escapement, and created the first type of a mechanical clock. So let us see how a metronome is going to work. So we have a metronome here in front of us, okay, and what I am going to do is to show you how it works. I am going to open up the casing, okay, and right now it is hold in position, and I am going to release it from this position. Okay. You note here that this part is actually the wrought part, and there is a end mass here, right. And we also know that the time period, though this is an inverted pendulum, but the time period t would be 2 pi square root of L over G. So that means the end mass does not actually play any other role, just to run the mechanism. However, the important thing is this length. Okay. So if the length is more, then the time period proportionately will be more, and of course it is square of it. Okay. And if the length is less, then the time period will be smaller. So it should be moving faster. So let us see. Right now this is the maximum position. Let us keep it, and let us look at it how it is going to work. So let us release it and see how the metronome is going to work. We see one important thing, that it is very periodic in nature. The motion is continuous, and it does not change much the time period. In fact, you can measure the time period also. So this is at the highest position, and if I change the length now, let us say I change the end mass position now to a much smaller length, and let us see how it is going to work. So let us just sort of give it a motion here. We need to give a little more energy to the system, and now you see how fast the entire system is moving. Why? Because the L has reduced, and square root of L, the time period got changed. Okay, it is very fast now. So this is something that is first thought up by Galileo, and then what happens for such a system is that there will be a sort of a dissipation of energy. If I take a pendulum and simply leave it from its uh, if I take a pendulum and simply leave it from its central position, the amplitude will gradually come down because of the damping of the air. Okay. So, what Huygens thought is that let us have a system which can continuously impact it. So, that is why this impactor is there, that actually gives a little bit of mechanical energy to the system, and so it never dampens so fast. So, this is how the Christian Huygens, okay, so his great role was to first develop this kind of a mechanical clock. Now, then this entire system is so simple that you can cast this, okay, and you can cast the second one. So, you can actually make the entire system in wrought iron. Okay. However, people later discovered that cutting this kind of a gear tooth is something which can be done with a better material, and that is how the brass came into picture. In fact, that is why the color is also given that way, that the geared part, the escapement part, later on got shifted to brass type of a material, which can give you a much more precise cutting and much better, because brass is harder. So, it will give you much better dimensional stability. Okay, the wear will be much less in such a system. So, this was how the mechanical clock evolution take place, and then from there we come to the industrial phase. In the industrial phase, you see the railways are moving, so everything has to be much more precise in terms of time. So, then at that time the clock also should be such that, let us say, for a duration of a week, the clock should not need the energy supply. So, it should have enough energy to survive at least for a week. So, how do we do it? Okay, there are a couple of innovations that people have done. The first important thing, of course, is to use a material which we will call tribological material. It is for the first time tribology came into picture. That means the wear should be so less and the friction should be so less that the whole system can survive for a much longer time. In order to do it, this time now from the wrought iron, the steel has already come into picture. So, people started using the high carbon steel as the pivot. Okay. So, this is also known as silver steel, okay, and ruby is used as bearing. So, this is made of ruby. Now, you know that ruby is a gem, of course it is. It is actually something called corundum Al2O3, but if Al2O3 is only used, then it would of course become very transparent. So, the color comes because of the chromium. So, a little bit of impurity, adding chromium to corundum gives you ruby. And look at the hardness of Vickers hardness test, the ruby's hardness. It is 1800 to 2200 in HP value, and compare it against steel. It is 600 to 800 for the hardness of steel, and for brass it is 100 to 150. So, naturally the shifting to ruby is something that would what would happen is that if you look at the Archard wear law, then you would see that the wear volume is inversely proportional to the hardness. That means, the more the hardness, the less will be the wear volume, and because ruby is so high in hardness, so the wear volume comes down, and hence the clock will survive for a much longer time. Okay. In fact, that is why you would see that in some of the good quality clocks it would be written that there are 7 jewels, 9 jewels. It is nothing but that how many rubies are actually included in the system in order to reduce friction, in order to reduce wear, in order to give it a much higher dimensional stability. So, that is how the ruby came into picture, but ruby is expensive. Another important thing I want to tell you here, that what could have been a better system than ruby? Can you think of it? Well, something which is much harder than ruby, that there is only one material, and that is diamond. Of course, it is even more expensive, right? But a very good clock, Rolex or something, would definitely have diamond there in terms of in the place of ruby as the bearing, to minimize the frictional loss, okay, because that will have almost no wear for a very long time. Now, then I told you that ruby is very expensive. So, people started to think that how to manufacture synthetic ruby. So, as I told you that ruby is very expensive. So, the question is that how do we manufacture synthetic ruby? Okay. So, you have to again use, of course, aluminum oxide, that is the important element, it Al2O3, and you have to use a little bit of chromium oxide, right. And then what you can do is that you can use either of the two process. One first process is called the flame fusion process or the Verneuil process, in which you are going to basically put the aluminum oxide powder from one side, let us say, okay, and the chromium oxide powder in a chamber like this, okay, in a chamber like this, and then you have to apply the flame, okay. So, hot oxyhydrogen flame. So, you have to apply the hot oxyhydrogen flame approximately 2000 degrees centigrade, and you will see that there will be melted droplets on a rotating pedestal. So, you have to have some kind of a system here on which the drops are going to come as I am going to apply a high flame, okay, of oxyhydrogen flame. And then this is a rotating pedestal, we generally call it a bowl, okay. And on this bowl, what will happen is that there will be a seed crystal, and on top of that seed crystal gradually the system is going to develop, and you can, as it is developing, you can of course bring it down and down, and at the end what you are going to get is a big single crystal cylinder of ruby. That is what you are going to get, and once you get it, then you can slice it. So, you can slice many part of it, and that is how you get this each of the single crystal small bearing of ruby that you can use in the system. Now, there is another way to do, and that is called Choralsky's process, which is more followed today. So, you have the raw materials Al2O3 and Cr2O3, and you melt them in a iridium crucible via induction heating. Now, what you do? So, basically you melt them. So, you have all these materials and you have melt them. So, this is a melt pool. Melt pool of what? Melt pool of aluminum oxide and chromium oxide. And now, from here you take a crystal, okay, dip it inside a seed crystal, and then you gradually slowly pull this whole thing. So, you can do it in a small area and you gradually pull it. As you are pulling, the crystal is getting developed and you are going to get a long cylindrical crystal from this process also. So, this is what is the Choralsky's process that you have to do. So, in this case it is top down and here it is bottom up, you are pulling and getting the system. So, this is how synthetic ruby got manufactured and became a part of the clock. Now, if you look at the modern watches, okay, materials for modern watches, they have many. This is a really puzzle of all the materials that we have accumulated over the centuries of knowledge. Now, a modern watch can be distinctly having a group of material which we may call it to be structural material. Then we have a group of material called display material. Then we have, of course, semiconductor with us, we have energy storage system, we have sensors, because a watch now not only has to keep track of time, but also have to keep track of various body conditions. So that you need sensors. Then you have tribological material, which is sometimes used for energy storage, etc. And then you need to have protective materials, and also there are many emerging multifunctional materials that is becoming part of it, which I will touch later. First, let us only see in terms of the structural materials and the sensor and energy storage materials, which are part of the modern watches. So, in terms of the structural materials, okay, that is the watch case, the bezel, the frame and the mechanical supports part, the first important group of material now is the stainless steel. Okay? And stainless steel has two common grades in it, that is grade 316L and grade 904L. It is for the first time in this course now I am inducing something to you which is beyond a common attribute that this is iron or this is granite or this is just simply wrought iron or this is brass, something more than that. I said not only steel, but it is a 316L steel or 904L steel. So, what does that mean? Okay. So, the first term 3, for example, in 316 is a series indicator. So, that indicates a 300 series group. In metallurgical terms, grade starting with a 3 is an austenitic stainless steel that possess a specific crystalline atomic structure that makes them highly ductile, non-magnetic and adaptable across a wide temperature range. You see, the watch has to work across a large temperature range. So, that is the first thing, that in the winter and summer the watch should not change its property. So, that is why the 300 series is basic minimum you have to have. Now, not only 300, then we are going for 16. 16 is a sequential identifier. So, that represents a specific chemical recipe within the 300 series group, and in this sequence 16 indicates roughly molybdenum should be between 2 to 3%. Okay. So, that is very important. Okay. Why? Because the introduction of molybdenum will give it much more endurance. And then I also said L here. Okay. So, L is basically low carbon, and that is something that is earlier days would not be there. So, that carbon should be definitely less than 0.3%. Okay. So, that all these things, if it is guaranteed, then we get a much more complicated but much more specific attribute of a steel, that is called 316L steel. Another possibility, which is more expensive possibility, is 904L steel, where 9 is not simple austenite, but super austenitic material, and then that 044 means it has a high level of nickel and chromium along with some added copper in it. Now, what 904L can give you is that it is going to give you a very high strength. Okay? So, that you can use the clock not only in ambient condition, but also you can use it as a diverse watch. That means you can go deep inside the sea, even then it will be able to withstand the high pressure and the watch is going to work. So, this is 316L and 904L. Typical density at the range of 8 gram per centimeter cube, that we know, one of the attribute. For the 316L, the strength is about 250, and for 904 it is about 600 MPa. So, you can understand that great strength is important, and all of them are having excellent corrosion strength. So, they are going to work for a long duration, they are going to absorb the heat and all these things. So, that is like the first material of our choice, the stainless steel. Okay. Also, I told you that it must have a non-magnetic performance, because the magnetic field also should not affect the working of the clock. The second choice would be aluminum alloy, because then it will be much lighter. Okay. So, for slightly cheaper systems, we can go for say 6061 or 7000. So, now new attribute for the aluminum alloy. For aluminum alloy, 6000 series such as 6061 actually use magnesium and silicon as their primary alloying elements, and it has excellent weldability, formability and corrosion resistance. You need all of them in terms of making the casing, making the watch casing. If I go for aluminum alloy 7000 such as the 7075 series, it has higher strength, but 7075 is difficult to machine. Machining is complicated because it has titanium in it. Now, if you look at it in terms of the density, this will be very light, 2.7 gram per centimeter cube. So, this is a good attribute of aluminum. Yield strength 276 MPa. So, that will be slightly, you are compromising with comparison to steel, but if you go for 7075, you get about 503 MPa. So, if you go back and check that you were here about 600 MPa and here you are about 503 MPa. So, that is quite a great achievement if you go for 7075. Now, the good thing is that it is even become better if you think of it not as simply the yield strength, but if you think of sigma y over rho. So, compare the sigma y over rho here, which will be, let us say, approximately 500 over 2.7 versus what we saw for steel, which will be again say it was somewhat bigger, right. It was 600. So, you keep it 600, and however, you have this as say 7.5 onwards. I am just keeping it approximately 600 by 8, okay, and let us say this is approximately 3. So, you can see sigma y by rho, how much it is going to happen. So, you are going to get 6 here and then 6 here. So, about 166 approximately, and what you are going to get here? You are going to get here 7 and then 40, so 5. So, you see sigma y over rho ratio is around 75, okay, for the steel, whereas it is much higher in this case, right. So, it is 166. So, it is much higher. So, it is a much better material in terms of the strength you are getting and the weight that you are sort of getting a lighter weight. If I go to the last structural material, then it will be titanium, and particularly no other attribute but then this titanium alloy Ti6Al4 vanadium, okay, which means you are going to have, in addition to all other things, you are going to have a percentage of aluminum and vanadium mixed with titanium. So, what you are going to sacrifice is in terms of the density, it will slightly go up, not as high as steel. Steel is 8, almost double, aluminum is 2.5. So, now that is go up, but then the yield strength is much higher. Okay, you can see from 800 to 1100. So, that is a great yield strength. So, this you will get a kind of a material which can withstand even higher pressure. It will be much more rugged system. Also keep in mind, so it has a high specific strength and it is going to have a high corrosion resistance, and titanium is completely biocompatible. Okay. So, all these things, and another interesting point is that it is hypoallergenic. That means the alloy contains no nickel, making it highly compatible with the sensitive skin. There will be no etching and things like that. So, you see, this is possibly one of the best material, though it is most expensive. That is why we have kept it as third point for structural materials. So, this is the way the evolution of structural materials only has taken place. Now, of course, I told you from the sensor's point of view, we have two choices. One is called the Pizzetti sensor and another is called the IPMCs. Okay. These two materials we can use for the sensing and for the energy harvesting. So, how it is going to help us? Okay. Let us say what will be the role of piezoelectric material? Well, of course, there is one standard rule for a piezoelectric material, that if you use quartz, okay, there used to be a quartz watch. So, for a quartz watch, if you can mechanically excite it, okay, what you are going to get is a very regular resonance in the system, okay, because of the electromechanical coupling. So, if you excite it mechanically in a regular way, you will get a regular electrical voltage out of it. Okay. So, that means if you have a quartz, let us say, is like this, and you are exciting it, okay, with some kind of a force, let us say, and it is going to create a V sin omega t. Okay. So, force creating voltage, and if this is of omega frequency, you are going to get a omega frequency in terms of the electric voltage. So, it will be so regular electrical signal out of it. Okay. That means, if you have a quartz watch, then all these gear and escapements you can throw away. That is why the quartz watch became so sort of cool at one point of time. They are not very high precision. So, that is one. Another role of piezoelectric material will be, if you look at the conventional equation of piezoelectric system. So, there are two equations which I will come up later on, that S, the strain, is short of, we can call it as let us say, S, the strain is S sigma, and plus you have d electric field intensity. Okay. And you have another one, that is d as d sigma plus you have epsilon electric field intensity. So, these are the two constitutive equations of piezoelectric material. Okay. So, this is strain. I will come back to all these equations at a later stage. I am just telling you how you can use it, and this is electric field displacement. Let us call it charge, density. Okay. In fact, it is this second one that is important for us. So, now what it does is that if you have a variation of stress, okay, then that variation of stress will create a variation of charge. Okay. And then that charge you can actually store it in a capacitor, and later on you can use it for battery. So, this equation can be used for battery. Okay. Also, another way it can be used, that is, say, we have pulse. Okay. So, there is a continuous pulsation happening. So, there is a change of stress because of it, then that will also create an electrical pulse, and that electrical pulse also I can use in terms of a smartwatch by keeping track of that what is my body pulse. Okay. So, this is how the piezoelectric material would work. And today there is also another group of material which is called triboelectric nanogenerator. In short, it is known as TENG. Okay. Now, piezoelectric material actually creates electricity because of pressure, but triboelectric material such as PTFE, PTFE is polytetrafluoroethylene, something that PTFE, polytetrafluoroethylene, okay, something that tetrafluoroethylene we use in our non-sticks, for example. Now, PTFE is an excellent electron taker. Okay, the fluorine can simply snatch electron. So, what happens is that, suppose you have a PTFE layer, okay, and suppose you have nylon here, or even human skin, but okay, say you have nylon, and then PTFE is going to snatch electron from nylon. Okay, nylon is a giver, donator, and PTFE will take the electron. If you stop it, let us say you keep a dielectric system here, this is a dielectric one. So, definitely there will be a voltage generation now, because the electrons it is going to catch. So, all the electrons will line up here, and all the positive charges. So, it is going to create a voltage. Okay. And now, this voltage is actually proportional to this distance. So, as there is a change of pressure, if you have this system, there will be a generation of voltage in the system. Now, it can happen from the normal change of distance, or it can also happen the charge density may change if there is a shear. Okay. So, if this common area changes, if there is a shear, so either from shear or from the change of distance, for both of them this will result in contact electricity, and that contact electricity can be saved and can be used in terms of charging the battery. So, the two important thing of today's smartwatch uses different material attributes, right. It uses the steel as one group, or titanium or aluminum, and it uses another group like such as smart materials, and there also you have two different material attributes, the piezoelectricity or the triboelectric nanogenerators in terms of creating the voltage. So, that is how the material attributes get created, and we tried to look into it through some simple examples of evolution of watch. And in the next lecture we will try to look at it in terms of evolution of materials for transportation systems. So, that is where we will end today's lecture. Thank you.